Hi, my name is Marisa Alba.
Hello, my name is Adila Roscoe.
Hello, my name is Danny Simpson.
And today we'll be sharing with you our research of the math behind optical illusions with our advisor, Dr. David Gove, for the SURE program of 2022. Optical illusions are created as a result of our brain attempting to visualize three-dimensional objects from a two-dimensional plane, allowing us to see the impossible. Using Dr. Kokichi Sugihara's research on optical illusions and our knowledge of vectors, we were able to recreate optical illusions into 3D prints. We use the software program Sage to calculate new vertices of 3D structures that would create an optical illusion from a certain perspective.
Onto the topic of vertices in 3D. Typically in 3 dimensions, we have solids. Within those solids, we have length, width, and height. In those dimensions, you can also find the volume versus the area in 2 dimensions. Certain solids have surfaces that are polyhedral, which means that the surfaces are non-smooth. With this, there are points, also known as vertices, that exist. And when you connect 3 or more edges, they help form the face of a solid. So here in our example, we have a figure in 2D, which it shows a rectangle. We know that you split the rectangle into 2, which represents 2 right triangles. Typically, when you look towards the surface, you want to count in a counterclockwise fashion, versus in 3D, depending on how you look towards the surface, they are also counted in a counterclockwise fashion. So on to the topic of points and planes. So here we have our formula as presented with an A, B, and C, and its coefficients next to it. Typically in polyhedral surfaces, you have what is called planes, and typically within planes, there can be a set of points that are found within those planes. So to find the equation of a plane, it involves finding 3 points, and from those 3 points, you take 2 associated vectors. From those 2 vectors, it's typically the distance between the first point to the second point and the first point to the third point. With these 2 vectors, you take the cross product of both of them. When you take the cross product, you get a vector, and that vector is called the normal vector to the plane, as represented in the formula A, B, and C. So in the formula, x naught 0, y naught 0, and z naught 0 represent the first set of points, or basically the first point. So in this example we have down here, we have the equation of a plane between 3 points, which after solving you get y equals x, with the normal vector being -1, 1, 0. As you can see in the illustration below, there is a small black arrow pointing to where the normal vector of the plane is at.
You're talking about Sage and STL code. So in the process of making our models, we had to have 3 vertices and 2 paragraphs that defined a shape for, well, each 3 vertices would create a triangle and 2 triangles would create a square. So we needed those to make the surfaces of our 3D models. And once we did that in STL code, we took that from our non-illusion version of the model and we put it in a Sage code. In a Sage code, we defined the vertices, and then we used the vertices with some equations to make the illusion version. And then once we did that, we put it into this little snippet right here, or on the left of your screen. You should see a Sage code example, and that Sage code example is the function that gave us our illusion version after we were finished with the math in later Sage code. Okay, now getting into our methods. So when we first start out, we start by making a non-illusion version of our models. We want to build something that looks like what the model should look like in our illusion. So to get the illusion, once we're finished with that, we take our created 3D models that are non-illusion, and we use some equations that we put into Sage, an eye vector, which is just like where we want the eye's position to be, or camera. So after using our eye vector, we put it in, we want our desired y coordinate, and we put it into Sage code. Yeah, sage code. And that would give us our new illusion version of our model. So after finding that, we again use sage code to transform the points that we got for our illusion version, and we transform them into STL code, which we then copy and paste, and that will give us the illusion model that we then print out. Okay, now to begin talking about our 3D prints. My 3D print is of two pillars that both have holes at the top. And these holes actually made it quite difficult when I started making this. So the non-illusion version was pretty simple. It was just like the first project that we all did together, and it was really fast. But once I got to the illusion version, that is where I had difficulties because I had to account for the holes and I had no idea how to do that. It wasn't until I talked to our advisor that I realized that I needed a matrix for both of the pillars, and that would help me to create the illusion version. And I do have examples of the Sage code and the STL, or the STL transformation code, I think. Yeah, I do. So that should give you some idea of what I had to go through to make my illusion and non-illusion versions of my model.
So onto my model. From above, it looks as if the roof is in the original version, which the shapes are rather symmetrical to each other, as it appears under the photo of at a certain angle, when in reality, the illusion photo of it, the points on the roof have been shifted to the right, and there is a dent towards the back of the roof. So when the angle is changed, meaning that when you go lower and closer towards the figure, there is no roof sticking out, but rather it looks flat and there's also a dent. The result of this would be blue marbles. Rather than falling off the roof, they cave in towards the roof.
So for my project, I decided to create this 4-pillar bridge that when viewed from a certain angle, it looks like each pillar is increasing in height. So my first step was to create the non-illusion version, which has each pillar increasing in height. And to create this illusion, I had to transform the heights of the 3 pillars from the non-illusion version to a height that would be lower than the first pillar. So for the second pillar, I decided to decrease it to a height of 3.5, since my first pillar was at a height of 4. So then pillar 3 was transformed to a new height of 3, and pillar 4 was transformed to a new height of 2.5. So in the equation that you see on the left shows me finding the scalar for transforming the rest of the new vertices of the pillars, or the tops of the pillars. And I inserted the scalars into Sage with their corresponding vertices to calculate the new vertices of the illusion version. So towards the right corner, you can see the illusion version from a different angle. And at the bottom, you can see the result. So from this angle, you can see that the pillars look like they're increasing in height, but in actuality, they're not. So that's why the marble is looks like it's going up the pillars. Some of the things we learned during the process was that smaller details in the STL code, such as spelling and spacing, were very troublesome. So we always made it our priority to double check our code before running it in the 3D viewer to avoid any mishaps. Some of the things we learned during the process was that the smaller details in the STL code, such as spelling and spacing, turned out to be very troublesome. So we always made our priority to double check our code before running it in the 3D online viewer to avoid any mishaps when converting this STL file into the 3D printer. We also learned that the order in which the vertices were listed was very crucial to the overall structure of the illusion. So if the vertices were listed in a clockwise manner, the surfaces would distort and create unfavorable results. Having to visualize where the vertices went was also difficult, but we soon found out that creating a blueprint of the structure made the process a lot smoother. Overall, these 4 weeks have been a learning process. where we learned that the smallest of details shouldn't be overlooked. Here are our references for the illusions that we created. Most of them were from Professor Sugihara, and others were from videos from YouTube. We would like to acknowledge Chevron for sponsoring the SURE program of 2022, and we would also like to thank the Fab Lab for allowing us to use their 3D printers to make these models. Thank you.